Okay. Hi Nidir, we'll continue with waves from where we left. Uh, yeah, so this will help us speed up the physics wala quotient. So I thought I'll make a video and get done with it. Okay. So yeah, so just a small recap. We discussed two kinds of waves, right? We said that if the motion of the particle is in the direction of the wave motion, then it's called longitudinal. And then we said if the particles are moving in a perpendicular direction, then it's called transverse, right? Okay. Other thing that we talked about was we described the concept of this parameters of waves, right? Which are we talked about wavelength, which is given as lambda. It is the it is the peak to peak distance or the crest to crest distance or the midpoint to midpoint distance, anything that you like, of the wave. Then we have time period, which is how much for every particle, how much time does it take to go up and down fully. Then we derive frequency, which is equal to 1 by time period. Apart from this, we have defined amplitude and a generic term, which is displacement, and maximum displacement is amplitude, right? We defined all of this, so this is fine. So let's keep moving. Okay, so the next thing that we talk about is intensity, like energy. So one thing to remember is energy is always carried by the wave and not by the particles themselves, because every particle is moving up and down, right? But the wave in itself is moving uh, right in the case of a transverse wave, right? So what happens is so the wave transfers energy. Now we can't strictly measure energy in waves. What we measure is something called intensity. Now intensity we say is proportional to power by area. So if there is some source that's emanating out some power, like say maybe a light bulb which is 20 watts. Watts is power, right? So that it spreads out over some area, right? So you have some intensity here. But if you go a little bit farther away, then the same light becomes dimmer here because it is spread over a larger area. So this power by area, so this area is larger, so intensity decreases. So if area increases, then intensity decreases. So this is something to keep in mind. So the farther you are away from a source, the less energy you will feel. So this is concept number one. And another thing that we talk about is intensity is proportional to square of amplitude. Right, very important concept, that you say that okay, if there is one wave like this and then another wave with twice the amplitude, then this will have 4 times the intensity and not twice. Alright, so just to keep this in mind. Okay, I can just read through a book for all of this. It is fairly straightforward, but yeah, just to keep things in mind. Then the next thing that you talk about is wave speed. So wave speed is actually an easy concept, that you have a wave of wavelength lambda, right? How fast is this wave moving forward? So for this point, like consider this point here. So right now it's this blue point here. Now right now it is at rest, right? When this wave comes in, so slowly this wave will move like this, right? At that point it would have moved from here to a little bit down, and the wave would come like this. So that means that it would have come up again, and then the wave would come upper. So that means it would start climbing again. So it had gone down, then gone down, then it came up, then it stayed stationary, now it is rising up, right? Like this is for that single particle, this blue particle right here, this big red dot. Okay, so how much has the wave moved in this distance? So in the one time period t, in t time, the wave moved forward by lambda. So it was here, and then in the new situation, wave would be like right here. It this same wave from here to here would move to this section in one time period, right? So we say that velocity of this wave. So the peak of this wave has moved from here to here. So this distance is lambda, and it has happened in a t amount of time. So the speed of the wave, we say, which is also equal to lambda, is equal to sorry, is not equal to lambda, is equal to v, is equal to the distance moved, which is lambda, in time t, and we know 1 by t is f, so lambda into f. So very important formula. The velocity of the wave is equal to lambda times frequency. Mind you, this is different from the velocity of the particle, which is constantly changing. Sometimes velocity is downwards and sometimes it's upward, but regardless of all of that, velocity of the wave is always to the right, which will be given by this thing right here. Very important formula for the rest of the physics thing that you learn. Okay. So this is one thing. That then we talk about one thing that we talk about is Doppler effect here. Doppler effect, as you said, is a little bit like counterintuitive in the sense. I'm sure you have heard about the example of police siren going. "Ooh." So like the idea is that it is not changing its frequency or it's not changing its amplitude, but because it is moving the source of the sound, you hear different things. So the idea is if you are giving stationary source, then these ripples are uniform. So A and B hear the same sound. But when this source starts to move, then A hears a different sound than B does. Because these, if you see the wave traveling in front, is much more squeezed. So when it's squeezed, that means its wavelength is lesser. And if wavelength is lesser and speed is constant, then according to this formula, if wavelength is constant and has decreased, so frequency must increase to keep the speed same. So which is why this guy hears a higher pitch sound. So something like that. So if you can imagine that if this particle is moving, is oscillating left and right, then at some point it will hear a higher pitch sound, then it will hear a lower pitch sound, a higher pitch sound, and a lower pitch sound, which is what exactly happens in that police siren. There is a sound source that revolves on top of the car in a circle. So sometimes you hear the pitch of the sound increasing, sometimes you hear it decreasing. So it depends on so for this, when this guy hears a higher pitch sound, this guy hears a lower pitch sound, and then when this will move backwards, then the opposite will happen. So this is the idea essentially. Like, so this kind of a demo, if you want to see this is, so you see that this guy is getting a lot more waves per second than the guy behind. It's much more rarefied here, it's much more compressed here. So wavelength is shorter, so frequency is higher, so he has a higher pitch sound. Similar thing happens if he is at the back. He receives less waves, so the frequency is here is lesser. Okay, so this is the Doppler effect. So in terms of formulas, this is how we talk about it. So we say that say naturally the particle, say that those waves that are traveling outwards at a speed v wave, right? That v wave is equal to lambda times f, right? Now we know this lambda naught has changed, so this lambda naught will become some new lambda, right? And we know that this frequency f naught will also change to some new frequency because of this motion. So we say that the new velocity will be given by v wave minus v source. So if say the it's moving towards this guy, so we say that maybe so we say that lambda naught, yeah. So yeah, so this will be the new speed. V wave, you added a V source to it. One second, this does not look right. Hmm. So let's look at what your book is saying. It's saying that so Fs is the rate of is the frequency of the source, right? So it's saying that if Fs is the frequency of the source, then velocity of wave, then this will be the new wavelength, that divided by F naught is then F nu, lambda nu. So we can say that uh, if it is, sorry, why did I make this one? So if this is coming towards, so if this is the wave and this is also the direction of Vs, then we see a compressed waves here, right? So that means the wavelength must decrease, so which is why our book says negative here. So this, the wavelength will decrease by this amount. So this will be the new wavelength, right? And then we can find new frequency also from here. So F nu will be equal to V wave by lambda nu. So V wave by V wave minus Vs into F naught, right? So we see that this factor is less than 1 because it's V wave by something that's V wave minus this thing. So this ratio will be less than 1. So that means the frequency has decreased. So here a decrease has happened and this one has increased. Lambda has increased. So opposite. What is happening? So this factor is greater than 1. Sorry, really sorry about this. So this has of course decreased and this has increased. Okay, but see, anyways, these formulas are always confusing. You should always try to remember what idea is happening and try to visualize. So you see that compressed wave, so it's smaller wavelength, higher frequency. So we just want to always make sure that the formulas are agreeing with what are we saying. So always remember how these things have come down. So observed frequency is this guy. So you always need to remember how this is the key equation. So what is the new frequency observed? So you might be able to find, you might be asked to find the change in frequency. I would recommend that you try both 3 and 10 here. Okay. And after this, the chapter is relatively simpler. The first thing that it talks about is the electromagnetic spectrum. We know that we'll talk about this in much more detail in your next textbook also. But electromagnetic spectrum, we know that it has both electric field and magnetic field that are oscillating, right? If so, we know that if an EM wave, an electromagnetic wave, travels in this direction, then we have electric field that goes up and down. But in the plane that's perpendicular, we see that the magnetic field also goes uh, in the XY plane. Like if it is oscillating like this, then it's in the flatter plane. So this is say the B field, and the other one is the E field, like that. So which is why, so this changing electric field, we'll see how it produces, like later we'll see how this changing electric field is producing this magnetic field, and changing magnetic field is producing electric field. So they kind of help each other out like that, and then they exist together. So this is the idea behind electromagnetic wave. Now if you start wearing this, so again here also we have this concept of a wavelength. Now if you keep varying this wavelength, you get all kinds of things. So how we used to talk about it is, you might get radio waves which are least dangerous. So you want to have the least, so frequency is danger in a way. So this frequency will be the lowest. You always need to remember. And then maybe then towards, then you have microwaves, then you maybe have infrared, then you have visible light, then you have ultraviolet, then you go further beyond, you have x-rays, and then finally you have gamma rays. So you can imagine that this frequency is highest, it's the most dangerous. So similarly wavelength here is the highest and wavelength here is the lowest. So this trend we need to understand. Okay, so the main important thing is this thing right here is the visible light. It's very small. It's only like from 400 nanometer to 800 nanometer. It's very small in the grand scheme of things. So like the everyone, so like the way that they show it is, so of course, so we talked about this. There are a few types, and then the speed will always be given as this, and the speed is very high for these. But then this is a constant for all the waves. This is the speed of light, as we say. Very important to know. Okay, so this is what we are talking about: radio wave, microwave, infrared, and then very small sliver is visible light. So this is almost everything. So everything that you can see belongs to this. So there are a lot of animals that can see in the infrared. So they can see different to us. The infrared cameras, right, which have a different view. There are few bat species who communicate in ultraviolet. So we can't even talk about that. So a lot of rays from stars, or these old stars, comes in microwave frequency. So our eyes can't see it, but we can have a special equipment, like a telescope or something that can be used to see these microwaves. I know it's funny how we are seeing using telescope to use microwaves, but that's how it is. Uh, your Wi-Fi band is in the microwave region. It's called 5 gigahertz or 2.4 gigahertz band. It lies in the microwave region. All your cell phone communication, Bluetooth lies right here in that band, 2.4. So of course your medical imaging rays lie here, which is in the X-ray rays, right? So there's a whole plethora of uses and different cases that people have found. But of course, like what is used to see, what is the aesthetic appeal, all of that lies in the only the visible region. One more thing about infrared is infrared has has that heating tendency in the body. So whenever, or water molecules in general, like wherever you have infrared waves, there it is generally seen that that part heats up. So that's one of those features of infrared that you should know. Ultraviolet, of course, because it is higher frequency, so it's a little more harmful. So which is why we put ozone blockers, right? Like UV blockers on our skin and sunscreen and all. Okay. So this is a very small sliver, as you can see, so it can vary a lot. Okay, and then this is what we talked about. And the last thing that we talk about is, so you should also read this. It's a nicely written section in your book. But the idea about polarization is, so this E field is going up and down, right? Yeah. So the E field, oh, so the E field is going up and down, and the B field is going like this. We said, right? So we can say that E field is going like this, and B field is going like this. If you look from the side, right? So now we can say that maybe this E field direction, this blue line, maybe it is in all directions. Maybe E field is also there in all directions. Of course, then B field also will be there in all directions. But this is how it is. So this light we call unpolarized light, where there is no direction of that E field, like electric field. is basically unpolarized. So what we do is we maybe put it through this. So we have this light that's there in all directions, and then we put it through something what we call a polarizer. So this, and then you have something that comes out as only oriented in one direction. It's like a pure tone. So like the example that your book gives is, say you have a string that passes through a slit and you're trying to move that string, right? So if you are moving that string perpendicular to the direction of that split, the slit, then that wave will not pass through. But if you move it along the direction of the slit, then that wave will pass through. So it's kind of like if you try moving it maybe in a circle, still what you will get there is only like vertical waves. So this is the main idea behind. So this is acting like a polarizer. So similarly for light also we have like, so the way that these work is there are long chains of molecules. So you have polymers in chemistry, right? So you check polymers that are extremely long and they're very well organized. So there's one sheet, then another sheet, then another sheet. So when you put light waves in this, so anything that's along the plane is observed and anything that's perpendicular gets passed on. So that way it selects one direction. So these are something that you see on your glasses, like you have polarized glasses. Every single LCD screen has a layer of polarizer material on top of it. So what you get out of any screen that you see is polarized light. In general, the light from the sun after a general is unpolarized, like the light around you, everything. But sometimes when it bounces off through water, it becomes polarized. So what I'm saying is this. So you have unpolarized light that's coming in and that bounces off water, and because of how that water reflection process takes place, what you get out is polarized light. So ideally what you can do is you can be a person standing here and you can have glasses on, right? And then when once you see this light, maybe it is oriented in this particular direction. So the glare of the sun that you see when you look at the water, so your glasses can filter that out. So as a result, you can, so this light then does not reach, like gets blocked by your glasses or by a polarizer. And as a result, you can see inside the water because you wouldn't be able to see the inside the water because of the sun's reflection, right? So this is how these kinds of images are captured. Like you don't see them, but if you're say wearing the right glasses, then you will have no glare in the water and you will be able to see inside the water because the light after reflection becomes polarized. So this is just stuff like this. So this is the idea that you have unpolarized light, you put a polaroid or a polarizer, and then it orients light in one direction. Then you have an analyzer, which is basically another polaroid, right? So if it's oriented in the same direction, so you have everyone has this transmission axis of a polaroid. So if those transmission axes are aligned, then whatever comes out of the first polarizer, it goes out of the second, right? But then if you flip it 90 degrees like they have, so the transmission axis is 90 degrees, then this polarized light is not able to go through. So this concept we embody it in Malus law. We say that maybe the angle between them is theta degrees. Then the intensity of the light, yeah. So the intensity of the light that comes out will be given as like this. So whatever is the original intensity into cos square theta. So of course when theta is zero, so they are both aligned. Cos zero is one. So cos zero is one. So it just becomes I naught, right? So the whole of light passes. So now if theta is 90 degrees, that means cos 90 is 0. That means nothing passes through, right? So I becomes 0. So this is Malus's law basically. It tells you that okay, if you have light coming in, if you have polarized light coming in onto a polaroid, then if you change it by an angle of theta, this is how the intensity will vary according to that angle of theta. So this is the graph you will see if you try keep rotating and you measure. So at 90 it will become 0. At 180, uh, at 90 it will become 0. right here. At 180 it will be again become I naught again, because it will be completely flipped, but it will be still be fine. And at 360 again. So very, very important to know these things. Okay, like this is the chapter, so we'll talk about it tomorrow as well, like what goes on. Okay.